Okay, so what we're going to be talking about today, if you bought a textbook, will be a very small portion. Like we're going to cover much more than what's in any introductory circuit analysis textbook, because the concept of linearity and superposition is actually an incredibly powerful tool that we can use. And what our textbooks call superposition is really just one small portion of that. So to prepare you guys as best as I can, we're going to cover all of it. Now, I say that we are going to be looking at this from an initial perspective very differently than probably anything you've seen in any of your classes, except for the few biomedical engineers who might have taken their linear systems and signals class at this point. Okay, so this is going to seem real wonky at first, but I promise that we're going to pull it back around to circuits and it'll make a significant amount of sense. All right. So the concept of linearity is the first thing that we're going to talk about. So let's say that we have a black box system. Where I have some input x1 of t and some input x2 of t. Told you this guy that this was going to be a bit weird. And as an output of this black box system, we have a signal y1 of t and a signal y2 of t. What this black box system is doing is acting on these inputs by way of a transfer function. Transfer function is simply the output relationship over the input relationship. Again, we're going to tie this back to circuits very shortly. All right. If this system is linear, then the system response must satisfy the following equation. So our transfer function h must act on our inputs in the following way. Alpha x1 of t plus beta multiplied by x2 of t must yield a response alpha y1 of t plus beta y2 of t. I am overwhelmingly aware that this looks like a bunch of mathematical and potentially Greek garbage I'm throwing at you that you have no damn clue what I'm talking about. Perfectly okay with that, all right? What's actually going on here is two very distinct properties are being satisfied at the same time, okay? The first of those properties is what's called the additivity property. That's not how you spell additivity. Additive. T. And the second property is what's called homogeneity. All right. So let's talk about the additivity property first. The additivity property states that if several independent inputs are applied to excite a system, the total response due to all of these excitations can be determined by considering each input separately while assuming all other inputs to be 0. While assuming all other inputs to be 0. So let me explain what that means to you from a system scale, and then we will directly apply it to an example problem. Okay. So let's say that I have my black box system where I'm just going to represent it with this box from here on out. And it has its transfer function h of x. If I apply an input x1 of t, I get an output y1 of t. Okay. If I take that same black box network and I apply an input x2 of t, I should get a new output, which I'll call y2 of t. Okay. So where the additivity property comes in is if I take my network and I apply both inputs simultaneously. So on the input side, I apply x1 and x2 of t. I should see that my output is a simple combination y1 plus y2. Okay. So if I apply either input independently, I get its respective output. But if I apply both at the same time, I get a combination of the outputs. So let's apply this to a circuit. And we're going to test things in a couple of ways, all right? Do I have enough room here? No, let's do it on this page. Sure. Got it now? All right. So we're going to solve a circuit in two ways. This is our circuit of interest. We have a 6-volt source connected to a 6-ohm resistor connected to a 10-ohm resistor. Then over here, we have a 9-ohm resistor. Here is our 2-amp source. So our inputs in this case are that 6-volt source and that 2-amp source. So they're playing the role of x1 and x2 respectively. And let's say that this resistor current, I sub x, is our output. Ignoring all of this hippy-dippy additivity property and linearity junk that I've been talking about, how would we solve this circuit based on our level of knowledge up to this class? Anybody have any thoughts? We're going to have to apply Kirchhoff's current law, maybe some Kirchhoff's voltage law, potentially Ohm's law, and all that kind of good stuff, right? So I would say, let's see. I'm going to call this current right here. I'll do it in a different color. I6 because it's the current flowing through the 6 ohm resistor. And for the sake of argument, because we might have to use this, I'll call this guy V6. And because we might have to use this, I'll call this guy V10. And because we might have to use it, I'll call this guy V9, like so, right? So that we have currents and voltages well defined for all of our resistors at a minimum, so we can probably apply Kirchhoff's voltage law and Kirchhoff's current law and Ohm's law anywhere and everywhere we could potentially need to. All right. So if our ultimate goal is to figure out what that current Ix is, one approach we might take is applying Kirchhoff's current law to that top middle node, this guy right here, right? So if we apply KCL, we would see that I6 plus 2 amps is equal to our current Ix. Anybody got any problems with that KCL relationship? We have a current of I6 entering the node from the left, a current of 2 amps entering the node from the right, and a current of Ix exiting the node from the bottom. Kirchhoff's current law, currents going in equal the current going out. Nothing wild or crazy there, I hope. We could write a Kirchhoff's voltage law equation around our left-hand loop. So we would have negative 6 volts plus V6 plus V10 is equal to 0. So we now have 2 equations and 4 unknowns. And we could use Ohm's law to kind of transform some of those unknowns into different unknown quantities, right? So over here on the right-hand side, let's call this guy our Ohm's law section. And we could say that V10 is equal to 10 Ix, right? R times I, or V is equal to I times R. And similarly, we could say that V6 is equal to 6 I6 using Ohm's law. So if we look at our first equation, I'm going to call this guy equation 1 and this guy down here equation 2. We could rearrange equation 1 slightly and say that I6 minus Ix is equal to 2 amps. And I could say that 10, excuse me, let me say 6I6 plus 10Ix is equal to 6 volts. You're correct. Thank you. Yeah. When I move the 2 amps to the right-hand side, I should get a negative sign, just like when I move these 6 volts from the left to the right. That's why I switched the sign. So thank you very much for catching that. Or working it the next way around would have came out very awkwardly when I had the wrong answer. So thank you. Let me double check our algebra here just so I don't make some other silly mistake, right? So I'm moving Ix from the right-hand side to the left-hand side, so that's where that negative sign comes from. I'm moving the 2 amps from the left-hand side to the equal side to the right-hand side, so that's where it gets its opposite sign. For equation number 2, I've moved the 6 volts or negative 6 volts over to the right-hand side. I've expressed V6 as 6I6, and I've expressed V10 as 10Ix. Just to make sure here, the current is flowing into the positive polarity terminal for both of those. So I'm using the correct Ohm's law relationship. All right. So I have a system of equations that I can now solve. So those of you who know how to use your system solver on your calculator, please tell me what value I would get for I6. And IX. All right. What'd you get for IX? All right, so negative 7/8 of an amp and positive 9/8 of an amp. All right. So what we were really interested in, and I'll put this in a red box. Is this guy right here? How difficult was it to solve for this quantity? If I hadn't been here telling you, let's do KCL here, KVL here, blah, blah, blah. Reasonably difficult, right? I'm sure some of you could have figured it out brute force method, but it probably would have taken you, let's say 5 to 10 minutes at a minimum. The way that I'm about to show you is going to be significantly easier because of the configuration of this problem, all right? So this is our method number one, doing it with our current level of circuits knowledge. Now let's apply the additivity property, all right? So what the additivity property allows me to do is analyze the circuit with only one source on at a time to determine what that value of IX is, and then add the results together. And I should get that exact same thing. So I'm technically going to be analyzing two circuits here. You may say, well, you're analyzing two circuits. That's probably harder, but I'll show you, hopefully, that it isn't. So let's talk about what it means to turn, let's leave our first configuration will be voltage source on and current source off. Okay. So with my voltage source on, I have my 6-volt source, my 6-ohm resistor, my 10-ohm resistor through which I'm trying to find some current IX. Bless you. And then my 9-ohm resistor. And I'm leaving my current source to be determined. All right. So let me ask you guys a question. What does it mean to turn a current source off? It provides 0 current. So we are looking to make a substitution here where we replace our current source with an element that allows no current whatsoever to flow. What do we know that forces current to flow to be 0? An infinite resistance, which is a fancy name for an open circuit. So to turn a current source off, we replace it with an open circuit. I will write that explicitly here. All right. So somebody tell me how to find what I'm going to call IX prime. Actually, it's going to be a portion of our total current IX. Somebody tell me how I can solve for this. Okay. Yep. Yeah, so 6 volts divided by 16 ohms should be Ix prime. So that should look like 3/8 of that. Effectively by inspection. Everybody okay with that? So since the 9 ohm resistor isn't part of a closed current carrying path in our circuit, it has no contribution whatsoever to the circuit's behavior. So we effectively have a 6-volt source in series with a 6 ohm resistor, in series with a 10 ohm resistor, and all the current flows in that one little loop. So it's 6 volts divided by the total resistance. Right? Now let's look at this same circuit, but with the voltage source off. So what does it mean for a voltage source to be turned off? It's supplying 0 volts. So we want an element that forces the voltage drop across it to be 0 volts. What is that? A short circuit. So we replace our voltage source with a short circuit, and then we redraw the rest. There's our 6 ohm resistor. Here's our 10 ohm resistor. Here's going to be Ix double prime. Here's our 9 ohm resistor. Here is our 2 amp current source. And I will write out here to turn a voltage source off. We replace it with a short circuit. All right, so I'm running out of room here on the bottom, but I think there's actually enough space for us to analyze the second circuit here. All right, I think I can fit it in down there. How can I determine that current, Miss Miguez, sorry.
So, how can we still have the current?
There's voltage in the system, just not over that short circuit. So it's not a dumb question, but it is something that's kind of difficult to understand. But you got to think back to Ohm's law, right? So V is equal to I times R, right? Well, R in this case is 0. So I can be anything it needs to be through a short circuit, right? So there will be voltages in the circuit because we have some amount of current passing through resistors and all that kind of stuff, and that's good enough to make things flow in general. But explicitly for the short circuit itself, Ohm's law has been satisfied since any amount of current multiplied by 0 resistance gives us that 0 volt drop. So effectively, if that weren't true, current couldn't flow through wires, right? Well, we're treating wires as if in this class as if they have 0 resistance. Really, it's very, very small in comparison to the other stuff. So that's a fantastic question. So if there is a circuit that you have with multiple voltage sources present, you can turn each voltage source off one at a time and analyze the circuit that way. Or you could do a configuration where it's, a couple of voltage sources on and the others off, as long as each source is on only once, you're good to go. So circling back around to my original question, how do we solve for this current Ix double prime? Current division, yeah. we have a known amount of current flowing into a network containing parallel resistors, right? So current division tells us that Ix double prime is going to be 2 amps times, this is going to be a little tight here, 1/10 ohms divided by 1/10 ohms plus 1/6 ohms. So let's see. So it's going to be 3/30 divided by 3/30 plus 5/30. 3/8 times 2, 6/8 of an amp. All right. Yes, sir.
Why do we ignore the 9 ohm?
Because we know that all 2 amps of current flows through the 9 ohm resistor because it's in series with the current source, not in parallel. So now I can say that my current Ix which would be the current with both sources on, is simply Ix prime, the current observed with only the voltage source on, plus Ix double prime, which was the current that we found with only the current source on. And if I add 3/8 and 6/8 together, what do I get? 9/8. Is that the exact answer that we saw when we analyzed the circuit with both sources on? It absolutely is. This will be true for any and every circuit that we analyze in this class, because all of the circuits that we are going to be analyzing are linear or contain linear components. So our sources are linear components, resistors, capacitors, and inductors are all linear components. It isn't until we get into circuits with diodes and transistors and stuff like that, which is not this class at all. Junior level EE classes will be the first time linearity breaks down on us. Okay, so you don't have to understand why you can do this so much as realize that it's an applicable tool. Okay. So now let's talk about the homogeneity principle. And I'm going to make a little table in the right-hand side here, okay? So I'm going to put input on one side and output on the other side, all right? And so what we saw was when we have 6 volts and 2 amps, our output was 9/8 of an amp. When we had the 6 volt source on by itself, our output was 3/8 of an amp. And when we had the 2 amp source on by itself, our output was 6/8 of an amp, right? That's a fair assessment of what we did previously, all right? So the homogeneity property says if an independent input is used to excite a system, scaling that input by an arbitrary factor alpha causes the output to scale by the same amount. So if we take our black box system and we apply some input x1 of t, which gives us some output, y1 of t. If we take that exact same system, now we have alpha multiplied by x1 of t, where alpha just needs to be a non-time varying number, okay? What's really interesting about that, so that means it can be real numbers. So we could double the voltage or double the current or something like that. It could be imaginary numbers, which means we don't know really how that behaves in circuits yet, but it's effectively shifting it by 90 degrees in the frequency domain. Or we could use complex numbers, which is a combination of real and imaginary numbers. And this still holds, all right? So alpha x1 of t must yield an output of alpha y1 of t, okay? So if we scale the input by some amount, we scale the output by the same thing. What is your question and where is your max? Wonderful question. Absolutely wonderful question. Does it only work for independent sources? Yes. So well, let me be clear about that. It will absolutely work on circuits which contain dependent sources. But the turning on and off of sources that we did a moment ago only applies to independent sources. Dependent sources are always left on in the circuit. That's a fantastic question. Yes, sir.
So we probably take a moment.
Absolutely, yeah. So the coefficient won't change, but the amount of voltage or current being supplied by that dependent source likely will because of the configuration of the circuit. Yeah. So you won't have like 5ix suddenly becomes 3ix or anything like that, but the value of ix itself probably changes from the varying configuration. All right, so what I would like to do now, we're going to take our original circuit and we're going to scale both of our inputs by a factor of 2. Okay, so that means that we have a 12-volt source and a 4-amp source now. Everything else is identical. So before we analyze this guy, what does the homogeneity property tell us our answer is supposed to be? 2 times 9/8 of an amp, so that'd be 18/8 of an amp or 9/4 or however you want to put it. So I'm going to add that. Sorry, what's up? Oh, thought I heard something on Zoom. So twice 6 volts plus 2 amps should give us 9/4. Let's see if that's true. So we're going to analyze this circuit with both sources on exactly like we did in our very first example. Okay. So I'm going to call this guy V10, this guy V6, this current I6, this voltage V9, although we don't actually need to use it. So Kirchhoff's current law tells me that I6 plus 4 amps is equal to Ix, which I can rearrange and say I6 minus Ix is equal to negative 4 amps. Kirchhoff's voltage law says negative 12 volts plus 6i6 plus 10ix is equal to 0, where I just went ahead and did the Ohm's law substitutions directly into this guy. And so this says that 6ix plus, oh, excuse me, 6i6 plus 10ix is equal to positive 12 volts. We solve for I6 and solve for Ix. Somebody tell me what you get when you throw this into your system. 9/4 for Ix. And it would be, let's see, 7/8 times 2, 14/8 for the other one probably. Yeah. Oh, negative 7/4, yeah. Over an 8. So our output scaled by a factor of 2 because we scaled our inputs by a factor of 2. Justin, stretching or question? Around the left-hand loop. Yep. So if we had to scale both sources by the same amount, that's pretty boring. So let's really mess with some stuff, okay? So in order for, Drew, what's up? Yes. Yes. So let's say that I scale. Let me hold on. Let me get to it here. Yeah. I scale the voltage source by a factor of -3, and the current source is scaled by a factor of +5. Okay. So here's my 6 ohm resistor. Here's my 10 ohm resistor through which I'm trying to find some value Ix. Here is my 9 ohm resistor. So what does it mean when I scale my voltage by a factor of -3? If I had 6 volts in my original system, I would now have -18 volts, right? So I could say that scaling my voltage by a factor of -3 is the same as putting negative polarity on top, positive polarity on bottom, 18 volts here. If I scale my current source by a factor of +5, then it's just 10 amps instead of 2 amps, right? So, sorry, 10, not 2. Thank you. So what should my expectation of my output be? All right. So when I had 6 volts by itself, I had 3/8 of an amp, right? So I would argue that -3 times that 6 volts should give me -3 times 3/8. Or -9/8 of an amp from that contribution. When I applied my 2 amp source by itself, I got 6/8 of an amp. So when I scale that by a factor of 5, I should get 5 times 6/8, which would be +30/8. And so from that, my expectation is that when I apply -3 times 6 volts and 5 times 2 amps simultaneously, I am going to get negative 9/8 plus 30/8, or a current 21/8 of an amp, if I did my mental math correctly. I'm going to prove that to you guys, but if you understand this, you know that you never have to prove it again. This is just how circuits behave, okay? So if I call this voltage V10, this voltage V6, and this current I6, I can easily see that I6 plus 10 amps is equal to IX, which I can rewrite as I6 minus IX is equal to negative 10 amps. For my Kirchhoff's voltage law equation, I'm going to have positive 18 volts plus 6 I6 plus 10 IX is equal to 0, which I can rewrite as 6 I6 plus 10 IX is equal to negative 18 volts. I solve these two, sorry. What do I get? IX. So throw it into your system solver. The only changes you have to make here are obviously the constants at the end, and tell me what it comes out as. Sorry, that was I6. Sorry. What did IX come out as? 21/8. Exactly what I predicted before I did a lick of circuit analysis on this guy at all. Right? So that's why the concept of linearity can be such a powerful tool. We could actually work any linear circuit using only 1 volt sources, 1 volt voltage sources and 1 amp current sources, and then scale everything to find the answer for any possible configuration of input signals. Okay, that's a pretty dang neat thing. Any questions? Any other questions on this? I know it sounds weird, so I'm going to ask you guys to try to wrap your heads around it with the in-class assignment problem.